Okay, last class we were discussing about the order of growth concept with respect to prime number concept. With the example of prime number, how do we find the prime number? So here we were searching the method which we have discussed was searching by divisor was the method which we have discussed in last class. We have seen the algorithm and what is the benefit of going instead of going till n values for searching for a divisor. Instead of going till n values, it is better that with the half of it we can stop. So when we are saying it is square root of n, we have already seen what is the complexity for finding the square root of n itself. So it is better if you remove, instead of calculating the square root part, if you take the square root to the other side of your equality, it becomes the square. So when you compare square with square root, with one step you will be able to get the square answer for your square procedure. So which one is better? The square, going with the square procedure is better, so that we can reduce the complexity part. So that is the reason why instead of calling the square root procedure, we just have called the square procedure. That is applying the square root onto n value. It is better we apply the square procedure onto the sample, that is the test divisor. So by which we can gain so much of computation speed could also be increased. And the complexity also will be reduced because the number of times which we have to call the procedure is also less. So keeping that concept, we have defined this procedure. So first we have defined with respect to finding the smallest divisor, where we have the sub procedure where we are finding the divisor. So that's looping concept has been applied in the find divisor part. Then smallest divisor, we were just calling this find divisor by saying that by passing the value, that is the starting value, which is to be as 2. And we have used this divide procedure just to calculate whether it is whether it is divisible or not to check. So this procedure, divide procedure, will return true or false. And as a main function, we have defined the prime procedure, because with the name of what logic we are applying. So with that same name, if you have, then only it will be easy for the users to use it. So prime procedure. So question mark. So usually in this procedures, whatever in this programming language, whenever you are saying it to be as question mark, it is like we are expecting it to be as true, false, something like that. Okay. So here, if you want a sentence to be displayed, then you can even do that. Instead of stopping with equal to smallest divisor n, if you want, you can display it, or you can even return a string. So that is what we have done it here. If you want display statement, you can use the display statement and you can display the content. Whatever content you have, that you have to put it within the double quotes. And display is a built-in procedure, so you are calling this procedure by using within the brackets. Or if you want to return a string, that is also possible. So you can directly return a string. Don't have to write display and all. So this particular string, once based on the condition, if it is true, it will return prime. If it is false, it will return not prime. Okay. So otherwise, if you want just the true or false kind of thing, then that is also possible. You don't have to write any if statement also. You can just have equality, smallest divisor, whatever value whatever value is getting returned from the smallest divisor, you are comparing whether it is equal to that same n. If it is equal to same n, then it will return true, saying that it is a prime number. If it is not equal to n value, then you can it returns false, saying that it is not a prime number. So for this, the complexity would be square root of n. Moving on to the next algorithm, that is the format test. So in this algorithm, what is the approach? What they are taking is this algorithm works with respect to the probability concept. So here, it just as per the theorem, it says that if n is a prime number and a is any positive integer, that means we are guessing for a number a, and that should be less than, it should be a positive number, and it should be less than n. So when you apply a to the power of n modulo n it should be equal to n itself. Sorry, it should be equal to a itself. So if that is the case, then we can say that chances of the number n being prime is high. So like this, you have to pick up for random numbers. And that random numbers, how many random numbers you want to pick, that you can decide. How many times you have to repeat this process. So as per this format test, this is what is the theorem says. So if you want to say that n is a prime number, you have to go ahead with picking up a random number a, and that random number should be a positive number, and that too it should be less than n. Okay. So just I will just explain with respect to the algorithm, and then we'll go and take up one example. So first you are asking the user to enter the n value, and from here you are just picking the random number which should be less than n. So that random number which will be generated, it is the procedure. We have named it to be as a. So by using rand function, you can do that. After getting it, you are calculating a to the power of n. So a to the power of n means, which is nothing but exponential concept we can apply. So the procedure which we have already defined, exponentiation procedures, we have defined the exponentiation procedure in 3 different ways. So any one we can use it, and we have to calculate modulo n. So that value modulo n you are applying. So calculating the remainder for a power n mod n. So once you get that, the remainder whatever you are getting, if it is not equals to a, that means your n is not a prime. If it is equals to a, that means we can say that chances of n being prime is high. Okay, still for both the cases, if it is equals to, if it is equals to means we are just saying that chances of we saying n to be as a prime is high. So that means once we have to conclude it, it is a prime number. We have to prove that the number of times we satisfy this condition should be high. So based on the number of times, we can decide whether it is prime number or not. So we have to repeat this step. Once we finish with one random number, repeat the same process. Pick another random number and repeat a to the power of n mod n. You apply, calculate the remainder, and check whether it is equal to that same random number. If it is equal to the same random number, then we can say that it is chances of the number n being prime is high. So like this, we have to repeat till we are satisfied. Okay, so that means when we are making it to be as an automated, we can tell that how many times you want to repeat this process. So you can set up the times, how many times this has to be repeated. So that we can build up the confidence for saying that your number n is a prime number. So this is like a probability case. So chances, this is like chances of n being prime or not prime. So sometimes we may even get the result to be as opposite also. There are chances if you are not repeating, if you are not doing the sufficient number of checks. Okay, so that is what is the last statement, what it was. By trying with more and more A's value, more and more A values can increase the confidence, of the result. We'll see this format test with 2 examples. When we pick up with n value to be 5 and n value to be 6. So first let's take up with n value to be 5. So what we are just taken the input value for which number we have to find the prime. So the n which is 5, we have to check whether 5 is prime or not. So we have to pick a random number a. So if suppose if your random number is 2, if rand function you have used and if it is generating the value 2, then what happens? Then we have to calculate a power n. So any of the exponentiation procedure we have defined, any one you can use, and you can calculate 2 to the power of 5 mod 5 which is 32 mod 5. So your remainder will be nothing but 2. So if your random number is equals to the remainder value, then we can say that chances of value 5 being prime is high. Okay. Next we are picking with the next random number. If it is 3, then we will be calculating 3 to the power of 5 mod 5. And the remainder which you will be getting will be 3 itself. So here which will be the value 3 is equal to the remainder and the random number which we have picked, both are same. Then we are just building our confidence to say that the number 5 is a prime. So if I am repeating, still I am repeating the process. If next time when I am picking the random number, if it is 4, we will be calculating 4 to the power of 5 and mod 5. So the remainder which you are going to get will be 4. So still we can say that the chances of being prime, number of chances of saying that value 5 is prime, it is high. So like this, you can repeat this process for how many times you can set it up. Okay. So like this, if you are getting all the chances or majority of the times if you are getting it is prime, then we can say that it is a prime number. Chances of it being prime is high. At the end, you can say that it is a prime number. Similarly, if I take for the example 6, and if the random number what I'm going to pick is 2, what happens? We will be calculating 2 to the power of 6. Mod 6 is being applied. We will get the remainder to be as 4. So 4 is not equals to 2. So we can say that it is not a prime number. The number which we have picked is not prime number. So do we have to stop it? No. We can repeat it. So if the second time when you are picking the random number, if it is 3, then we will be calculating 3 to the power of 6 mod 6. So now if you see, the remainder what you got is 3. So that means we are whenever we get 3 is equals to 3, we say that the chances of a number being prime is high. So can we conclude it's a prime number? No. So that's what we are saying. This algorithm works with respect to the probability concept. So the next time it is 4 equals to 5. The remainder will be 1. So 1 is not equals to 5. So like this, we can say that it is not prime. So if it is a prime number, you have to make sure that the number of times chances which you are having, which you are getting should be the remainder as well as the random number whichever we have picked. It should be equal. Okay. If you are getting not equal, then we can say that it is not a prime number. Okay. If suppose for this number 6 you are taking, and if you are doing this process only for one time, and if the random number whatever you are taking, if it is 3 or 4 by chance, what happens? It will end up saying that chances of this number 6 being prime is high, right? So based on this conclusion, you will be concluding the number 6 to be as prime. So these type of algorithms, that is like we say that with respect to the probability concept, it is working. So for these type of algorithms, what you have to do is you have to make sure that the number of times it iterates should be you have to just analyze and you have to calculate the minimum number of times at least it has to work. It has to iterate. Otherwise, if you are iterating it for less number of times, then chances of ending up getting wrong results are high. So to avoid that, for whichever this probabilistic type of algorithms, you have to make sure that it iterates for some number of times. So how do you come to a conclusion how many times it has to do is based on some what is the maximum number of values which you can give. So based on that, how many times it has to iterate. So for some numbers if you can calculate, and accordingly you have to decide. So these type of algorithms we call it to be as probabilistic algorithm. this, let's start defining the procedure. So when we are defining the procedure, so first we can start defining the procedure. We have to okay. So when we start defining the procedure, so now see, this is the algorithm which we are having, right? So in our algorithm, we have to we have to ask the user what is the prime number which we want to calculate. That will be our main function. From that, we have to pick the random number. So we have to get a random number, and that random number should be shared. So from main function, we can pick a random number and we can pass it to another procedure. So that can be another procedure. And inside this, what happens? We have to calculate a to the power of n modulo n. So when we are having, we have already defined the procedure for how to calculate a to the power of n. So we have defined three ways, right? One is linear recursive process, which generates the procedure. First one which we have defined, it generates linear recursive process. The second exponentiation procedure, whatever we have defined, it generates linear iterative process. The third one which we have defined, it generates linear, it is like, it will be logarithmic times. It generates linear iterative fashion itself, but it will be, the execution is much faster when compared with the previous one because we are applying the square concept. Remember, where we are calculating whether n is even or odd. Based on that, we are applying the square. If it is an even number, we are dividing it by half. N is getting divided by half, and we are applying the square onto it. If your n is an odd number, b to the power of n. If n is odd number, we are applying b multiplied by b n minus 1. So that your number b to the power of n, that n will become an even number. So which one will be the better one which we can apply for this when we are calculating a to the power of n? The complexity should be less. So it is better to go with the third one which gives the logarithmic results. So the complexity, the order of growth which has given log n will be the one which is better. So keeping that, so since we have already defined that procedure, we can directly use it, and the name which we have given is exponentiation mode. So where we are having b, n and m, we need one more variable here. This is for just for random number concept. So first we are comparing whether your n is 0. If your n is 0, then we can return directly the value 1. Otherwise, if it is an even number, then what we have to do? If my n is even number, then I am calculating, I have to apply the square concept. Square onto what? Square onto whatever number I'm getting it from exponentiation of b, n by 2 and m. And for which one I'm applying the mod? I'm applying reminder, I'm applying it with respect to m. Because here each time in this exponentiation mode, each time I'm calling the n is getting reduced by half. But for applying this reminder concept, I want this m value. I want whatever was my previous n, that has to be maintained. So for that reason, I am maintaining this m, which is nothing but n itself. So when I am calling the procedure, that time I will be passing the same n itself at the initial point. If it is not an even number, then what I have to apply? I have to apply b multiplied by b to the power of n minus 1. So if you see here, I am calculating b multiplied by b to the power of n minus 1. So whenever I am saying, once again I am calling the procedure because it is b to the power of n minus 1. So I am calling this exponentiation mode procedure whereby b remains same and n is getting reduced by one time. M, which will be nothing but the same n, which I have to maintain it. And that value I am applying the reminder part. And then whatever value I'll get, that will be returned. The reminder value will be returned. So this exponentiation mode, is nothing but you are calculating a to the power of n mod n. So I have just redefined the exponentiation procedure, which we had defined it as the third one, which returns the logarithmic concept one, the complexity which gives us the logarithmic one. So I have made use of that exponentiation procedure. Along with that, I just have applied mod n concept also. So for getting mod n, I have applied this reminder part for even if your number is an even number or if it is an odd number. So just for explanation purpose, I just have made a procedure call. I'm just calling this exponentiation mod procedure where my b is nothing but value 2, n is 5, m is also my 5. Why? Because I just wanted throughout this procedure, I just wanted to maintain the n value. So that is the reason whenever I'm calling this exponentiation procedure, whatever is my base that will be passed and n and m will be initially the same. Where my n each time it is getting called, either it will be reduced by half or it will be reduced by one time. But my m I will not I'll not modify anything so that I can apply this reminder procedure with respect to m value. Okay, so reminder, first time when I'm calling, I'll check whether my n 5 is an equals to 0. No, it is, then I will come and verify whether it is an even number. No, my 5 is not an even number. So it comes to the else part. In the else part, we will be having reminder multiplied by 2 which is nothing but my base, this part, multiplication of base, and I'm calling this exponentiation procedure. So exponentiation procedure where my base remains same 2 and my n is getting reduced, it will become 4, my m will remain same. And what is my m here? It will be this m, which is 5 itself. Okay, so I'm expanding this exponentiation mod here now. So all these things will come as such. I'm once again expanding this exponentiation mod. So first again I'll be verifying whether my n is even. N is 0. 4 is not equals to 0. After that I will be verifying whether it is equals to even. 4 is even number. Yes, it is an even number. So what will happen? I am applying reminder procedure. So reminder procedure followed by square. I just wrote SQ so that I can save space. So SQ is nothing but square. I'm calling this exponential mod procedure where base will remain same 2 and I'm reducing it by half. So 4 by 2 which is nothing but 2. M will remain same 5. And this 5 is the one which is there at the end. So like this I keep calling my procedure one after the other. So by the end, what will happen? Once I get complete the exponentiation, if you see here, from here when I expand it, I'll get my 2 to be, 2 is an even number, so 2 divided by 2, which will become 1. Rest all, but this is getting applied. After that, once it is 0, it is just returning the value 1. So first what it does 2 multiplied by 1. It will return 2. So you will be applying reminder on 2 with 5. So 2 by 5 when you do, what will be the reminder? It will be 2. So you are applying square onto 2. So which will be 4. Right? After that you are applying reminder procedure 4 with 5. So 4 with 5 reminder procedure which will be 4 itself. After that you are applying square. So for 4, 16. So 16 mod 5 again. So 16 mod 5 which will return the value 1. So 1 into 2, so which will be 2. So 2 divided by 5, the remainder will be 2. So like this, you will be getting, this is how the execution is happening. So at the end of this procedure, you will be ending up getting the remainder, that is, which is nothing but a to the power of n mod n, the output for this. So for that purpose, we have made a small modification onto the exponentiation procedure, which we have defined in which achieves the logarithmic, the order of growth, which achieves logarithmic. Okay.
Ma'am,
Yeah.
Ma'am, I had a doubt. In this language, how are we supposed to define the procedures, ma'am? Like in the previous examples, we took like each small section of implementation, like a certain function, and we put it into a procedure. We made it as a procedure. But here we are actually combining two things and making it as a procedure. Like, is there a general pattern to follow or something? Like, uh, was I clear,
Uh,
ma'am, with the question?
yeah, you are saying like for this purpose, I have applied this exponentiation procedure. I have just modified it.
Yes, ma'am. So what I was asking is, can we just write another function just modulo and where we do remainder of exponential a power n and n, like instead of
That is also
having
possible.
no, ma'am. Like
That is
which
also.
is better? I'm asking, ma'am. Like out of these two, which one will be better?
Which one will be better is this one will be better. Why? Because first time you will be calling this if you are in whichever way you have told us, like we have a say only for this concept I'm saying we have a main procedure. From main procedure you are calling a sub procedure where you will be picking up random number, and from there you will be calling exponentiation procedure where you will be returning a to the power of n. Once that value you get, you will be you will come back to the second procedure, that is the sub procedure, and you will be calculating a to the power of n mod n, right? And uh, um, uh, that reminder value you will be taking, and again you have to iterate. You are getting my point? Again you have to iterate with the next random number. So the method which you have told, it will be little more that is like a little more complex. Two three procedures has to be defined again.
Okay, ma'am. Yes, ma'am.
Main procedure, from main procedure you are having sub procedure. In that sub procedure, which should this should be iterating with respect to each random number, that is like how many times you want to iterate, that you will be fixing, and it has to iterate. Okay, along with that you will be uh, 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 once that is written, uh, after that along with that you have to you will have another procedure which where you will be calling exponentiation procedure. So you will have three procedures only for this part. If you just write it down, it will be more clear for you.
Yes, ma'am. Yes. Like what I told was we already have the exponential procedure defined, no, ma'am.
uh,
So only for all that we're doing is just check if a power n mod n, like find what is the value of this one. We're not
mm,
comparing that anywhere, no, ma'am. So what we can use is we can define another procedure, something like a mod procedure, and inside that we can call remainder of exponential a and n, uh, that result, then n.
mm, mm.
So
Then also it requires two procedures.
yes, ma'am. That was my confusion. In the previous question, the last question that we were doing, the
Mm,
divisibility question, like
mm,
checking for small divisor and the smallest divisor and things, we
mm,
didn't need two three procedures there, ma'am. We took two three procedures there to take each step by step, and we put it into a
mm,
procedure. So
mm.
similarly, I'm asking, like, is there a standard way that we should follow? Like, should we make it a small procedures, or should we club two three functions together and write?
There is no standard way. It is like if whichever procedures, if you feel like it could be reused, those things you can make it to be as a module.
Okay,
That
ma'am.
was the only intention. Okay. There is no specific way of defining it.
Yes, ma'am. Yes.
Okay. This is the one, right? Which I was talking about. That same exponentiation procedure which we have defined, directly called it. There I had made use of here I have made use of three parameters, three arguments, and I have done here the same thing. We have done it by using two procedures, whatever you have said. Exponentiation, I'm just calling it here with the reminder one.
Yes, ma'am.
Okay, here also it is a power n mod n. Instead of making it to be as two procedures, I made it to be as a single procedure. That is the only change. I just gave you the example. What Vishnu was asking, this one and the previous one. That's it. So there are three arguments. Here two procedures. There one procedure with three arguments. Here two procedures. Okay. So next one, which we had to pick up for the random numbers. So for picking the random numbers, we have a procedure which will help us pick the random numbers. So when we have to pick the random procedure will be returning what values starting from? It will return a random procedure, that is the random function. Here we have a built-in procedure called random function. So whenever we are calling this random function, if you pass a value, say random 5, if you are passing, it will return any number between 1 to 4. That is 1 to n minus 1. So any number between 1 to n minus 1 will be returned. So since it is the one which we are applying is for prime number, and we know that we don't have to pick up the number which is getting divisible by 5, that which is being divisible by 1. That we know already, right? Any number which will be divisible by 1. So we don't require any number. If it is 1, we don't require 1 as such. So for that reason, what we have done is we have put one try procedure where we are calling this exponentiation procedure and we are equating it. Sorry, this was not there. We have defined format test procedure where we are taking the n value, inside which we have defined the try procedure. And here we are just comparing whether whatever is your a power n mod n, whether it is equals to the same random number or not. And inside this formats test procedure, we are calling this try procedure where we are using this random procedure and we are getting the value. So try procedure where we are adding this by using this random procedure, what is the value which you will be getting? Random of some 10 if you are passing, it will return any number between 1 to 9. So we don't require any number. If it is 1 by any chance, we don't want this value 1 because we know that any number will be divisible by 1. So what we can do to avoid that getting 1, what we have done is we just added the number with 1. So plus 1 we have done. So try plus 1 plus 1. So by any chance if the random procedure is returning 1, you can ignore that. So for that reason we have done this plus 1. And in this random procedure, I am not passing n value as such. I am just passing n minus 1. So that you can avoid getting the same n value also. Because random procedure is going to return n minus 1. 1 to n minus 1, any number it can return. So when I am saying if my n is 10, in this random procedure, I will be passing random 9. So what happens? This random function can return any number between 1 to 8. Okay. And I have what I have done to avoid getting the value 1, I am just adding plus 1 here. So that is the only logic here. That is the only purpose for adding this plus 1 here. Okay. Hope this part is clear. Why we have added +1. I'll just repeat. By using this random function, which is a built-in function, if you are passing random of n, if you are passing, it will return any number between 1 to n minus 1. So both are inclusive, okay? Chances of getting the number 1 as well as chances of getting the number n minus 1 is there. Now, since we are applying this random function to for calculating it for prime number, and we are applying the remainder and all, so we know that if your random number is 1, it will be divisible, right? So to avoid getting this random number 1, what I have done is, instead of passing random of n, I have passed random of n minus 1. So say if your number is 10, I'm just passing, when you're from this random procedure, I'm just passing random of 9. So what happens? This random function can return any number between 1 to 8, right? Inclusive. 1 as well as 8 is inclusive. So to avoid getting 1, we have to ignore the value 1, right? So to avoid getting the value 1, what we have done is we have added +1. Yes, sir?
Any idea where they will put these things?
No, sir. It's better you check with Rajesh, sir.
Rajesh, sir.
Yes.
Thank you.
Sorry, students. I was just telling about to avoid this +1, we have to add +1 to it, and I'm calling this try procedure, where it will be calling this exponentiation mode procedure. It equates. Here I have made use of the procedure which I have called with the 3 arguments, which returns the a power n, mod n will be returned, and we are just comparing whether it is equals to a or not. If it is equals to a, it will return true, otherwise it will return false. So now we have to decide with respect to how many times it has to iterate. So for that purpose, we have just defined a procedure fast prime, where you are asking the user to enter get the n value, whatever the user prime procedure where the user has entered n value, that procedure that n can depict, and how many times it has to iterate. So based on the times, you can decide whether it is prime or not. Once the time reaches 0, you can decide it is prime. Otherwise, you are calling this Fermat's test, which we have defined just now. If it is based on whether this is equals to or not, it keeps calling this fast prime procedure with the same n value, and the time would be decremented. If this condition and this condition is not satisfied, then what happens is it will directly come and say that it is not a prime number. So this is what the Fermat's test algorithm works. So that algorithm has been converted into a procedure. So now if you see the complexity part, the order of growth, the main logic which we are having here is a calculation of a power n mod n. So that is the place where most of the computation exists. So here the algorithm which we have used for calculating a power n mod n, what we have done, we have applied with respect to even or odd. So since that is the major portion, rest all will be iterating based on the number of times. So whatever time, how many times it has to iterate, that based on that value, it will be iterating. So here, since it is the exponentiation is log n, so here also the order of growth will be log n. Okay. So that's it about Fermat's test. So I'll stop with this.